Hello everyone, this is MOHAMMAD ASAD AMIN, lecturer in Physics, Education and Literacy Department. Today I would like to deliver you a lecture on Michelson interferometer, chapter number 9, first year physics. I hope you will find this lecture interesting and informative. Introduction. Michelson in 1881 invented this interferometer to measure the speed of the earth relative to the ether, and he didn't find anything. In order to verify the wave nature of light and to measure the wavelength of light or to observe interference of light, Michelson invented his famous interferometer, in which he divided the light from single source into two parts with the help of semi-silvered glass plate. The idea behind this interferometer is to split single beam into two and then recombine. Observer sees interference pattern projected onto a small screen. By moving one of the mirrors, the observer can change the path length difference. The consequence is a shift in the interference pattern. Construction and working. Michelson interferometer consists of two highly polished plane mirrors, M1 and M2. The mirror M1 is fixed, whereas the mirror M2 is movable, as shown in the figure. In addition to this, it has a glass plate C which has a thin coating of silver on its right side. This partially silvered plate is called beam splitter and is inclined at 45 degrees relative to the incident light beam. It has also another plate D which is identical to plate C, except it is not silvered. Its purpose is to ensure that the beam 1 and the beam 2 pass through the same thickness of glass. Therefore, it is known as compensating plate. This is particularly important when white light fringes, colored fringes are desired. A monochromatic beam of light from an extended source of light falls on the half silvered plate C, which is beam splitter. A part of the light is reflected from the silver surface of the beam splitter C at point P to the movable mirror M2. After reflection at M2, it returns to the observer eye through the plate C. The remaining part of the light passes through the silvered surface of the plate C, continues its journey, passes through the compensating plate D, and finally falls on the fixed mirror M1. The light is reflected back from the fixed mirror M1. It passes through the compensating plate D on its return journey, and finally it is incident on the silver surface of the plate C, from where it is reflected to the observer eye as shown in the figure. After reflection from mirror M1 and M2, the two beams eventually recombine to produce an interference pattern which can be viewed. Now suppose then extended source is monochromatic of wavelength lambda and the mirror M2 is then moved a distance lambda by 4. The path difference changes by lambda by 2 because as the mirror is moved by distance lambda by 4, the ray 1 will travel twice the separation between M2 and M1, and a dark ring will appear again at the center of the interference pattern. Thus, successive dark and bright rings are formed each time M2 is moved a distance lambda by 4. The wavelength of light used is then measured by counting the number of fringes shift for a given displacement of the mirror M2. If the displacement is represented by d, then if m is several thousand, the displacement is large enough so that it can be measured with good precision, and hence the precise value of the wavelength lambda can be determined. Now this could be more clear when you suppose that you start with the two beams in phase and look at the position of a bright spot, then modify one of the two path length. Bright spot will not be bright spot anymore. They will be bright spot again when the total path length difference is lambda. In simple words, you can understand this thing as the mirror M2 is moved by a distance lambda by 2, the path length will be twice, which is equals to lambda. So this will happens again at 2 lambda, 3 lambda, etc. In general, if we change one of the path by d in order to have a bright spot back in its original position, we must have 2d is equals to m lambda, or d is equals to m lambda by 2. From this equation we can find the wavelength of light as lambda is equals to 2d upon m, where m is equals to 0, 1, minus 1, 2, minus 2, so on and so forth. So in this way, Michelson interferometer help us to determine the wavelength of light.